Okay, I think we're good to go. So we got two classes today, and I think we'll need them both to cover these topics. And by the topics I mean we will talk about stuff that we've been working with already, like you know how to scale an object, right? We know how to rotate it, and we also know how to translate it or grab and move it somewhere else. Now all these things are built into Blender or any other 3D modeling tool. It's very much a common thing. But in order to do these things, something has to be done underneath this whole tool. So there's some programming implementation behind it, and you need to know what's the math behind it so that if you were to develop a tool like Blender, you'd know how to do that. Okay? So what I want you to realize is, let's have a quick look at what happens over here. Say we are given this cube, this default cube, which has a length of 2 units on each sides. And if you look at the coordinates, we know how to read them, right? If you go to the properties tab, you see that well, let's look at one very simple example, the positive ones. This vertex has coordinates 1, 1, and 1. Let me zoom it up and confirm that. So right up there you see that the x, y, and z values are 1, 1, 1, and 1. Now if I were to scale this up, this entire cube, if I wanted to make this twice as big, how do we do that? How do we do it in Blender? How do we make this cube twice as big? Yes, we scale that. So S for scale and 2 for twice as big, right? Okay, let's do that very quickly. So I'm going to select all the vertices because I want to scale up this entire cube, and I'll just say S2. Okay? The very same point that I had selected before, if you look at the just a bit. So if you look at the coordinates right now, let me zoom up one more time, you'd see that it has changed to 2, 2, and 2. So there is certain bit of math involved that converts 1, 1, and 1 into 2, 2, and 2. It's a very straightforward one, but there has to be something in there. Another example, let us take this cube, this entire cube, and let's say I want to move it along the x-axis 2 units. How do we do it? Now I just want to move it along the x-axis, but I want to move it exactly 2 units. How do we do that? G, and then Gx2, thank you. So Gx and 2, hit enter, that's what we get. And if you look at the same point, now, well, not this one rather. Now the point says 4, 2, and 2. Okay? So if you translate this, or if you grab and move that, G for grab, right? If you grab and move it along x-axis, only the x values change. The other things, they don't change. And you only need to add that. For scaling, we saw that we multiplied it by 2. Okay? And now if you move along the x-axis, we're not multiplying by 2, because if you did that, then we'd have how much? 2 times 2, 4. Well, actually, that's a very bad example because you get the same value. Alright, but it's actually not a multiplication because you're not multiplying by 0. Oh, we didn't move along y and z, so the movement along those things were 0. And certainly we didn't multiply 2 by 0 because that would give you 0. So what we did is we added how much we moved along the x-axis, how much we moved along the y, and how much we moved along the z-axis. So just to show you that it is indeed the case, let me select all these vertices, and I'll just move along the z-axis. Alright, so you see that this is coming up, and if I click on this point now, you'll see that the z value has changed, and the other things, they haven't changed. So this translation or grabbing effect only affects the axis that you move along, and it only adds that much to the movement, the actual coordinate rather. Or if I go freeform, if I select all these vertices and just press G to move it like that, you'd see that all these values, they change, alright? So depending on how much you move, it will change. And the scaling, this translation thing, you have looked at it before. We have covered that in another course. It's called coordinate geometry. Okay. So I'll bring that up, and I'll show you how things are different over here and why they need to be different also. One last thing before we move on to developing the formulas. We know how to rotate stuff, right? So if you rotate around the pivot point, right now the 3D cursor, if you rotate around the 3D cursor, you see that we can rotate something like this. So it will definitely change the coordinates of the same point, and you see that the values, they have changed. So in coordinate geometry class, you probably developed these formulas, or the formulas were given to you, and you just use them to calculate the final destination of a point. See, what we're doing over here, I mean, we're doing all these things on a cube, but it doesn't have to be a cube, right? It can be any object for that matter. It can be our good old monkey head. Because we can apply the same set of things. We can scale it up, we can rotate this, and we can definitely grab and move it around, right? So the same logic or the same math applies to the cube, and also on this Susan monkey head. So what's really the main issue over here? What we're interested to find out is how a polygon moves, because all these things are made out of polygon mesh. So if you can define it for a polygon, it can work for anything really. It can work for a monkey head, it can work for a cube, it can work for a cylinder, anything for that matter. And if you look at the polygons, what are these polygons made out of? Vertices or points, right? So if you have a sequence of points, you can make a face, and that's actually a polygon. So essentially what we'd be interested in is to find out how a point moves from one place to another. Say our previous point was P, and now it moved to P prime. We want to devise formula for each of these things. This one was a very simple translate, right? But we could also scale things up. So this thing, this point P, could also go there depending on the scaling effect. Now, if you know how to do it for 1 point, you could definitely apply the same thing for 4 points. Is that clear? And if you can do it for 4 points, that also means that you can do it for an entire polygon. Okay, so that's the angle that we'll be working, that we will find formula for each of these things. You'd find formula for translate, rotate, and scale. Okay, and if we can do that for one of these points, we'll be able to do it for the entire polygon, and if we can do it for an entire polygon, we can do it for all these polygons that make up this 3D mesh. Is that clear? So before we go any further, let us just revisit what we learned in our coordinate geometry. So I'll be just looking for formulas on Google to see how we did all these things. So let's like translate formula, 2D translate formula. It's a 2D transformation. We got a tutorial over here. Because I'm not sure if you have learned the 3D stuff in Coordinated Geometry Math 1024 course, but definitely have learned this, that if you are given a point Pxy and you want to move it to another point P prime, and you move it along the x-axis by tx units, in the y-axis by ty units, then the destination point is going to be P prime as x prime y prime, and x prime you can find it by x plus tx, and y prime is y plus ty. Have you guys seen this before?
Yes, sir.
Okay. Alright, so for rotation, we'll be developing these formulas. Actually, we'll build each and every one of these things in class, but I just wanted to give you a quick reminder of what you have seen before. Let's say you have a point P over here, and you move that point by theta degree above the origin, so it lands over here to P prime. So what are the things you know? You know the x value and the y value, the original location of the point, and you also know how much you rotate it, right? The theta is known. So what we need to find out is x prime and y prime. How do we find that? We find that through this formula, x prime equal to x cos theta minus y sin theta, y prime equal to x sin theta plus y cos theta. Memorizing these formulas is definitely not the goal. We're not going to memorize them. We're going to develop these formulas in class. Okay. Whether you memorize them or not, it's up to you. I mean, in terms of exam, you don't have to worry about that. You can bring in your cheat sheet and use that however you need. The scaling factor is really very easy. You multiply by the scaling factor. So if you have different scaling factor in two axes, we can define them by Sx and Sy. So you multiply the x part with Sx, the y part with Sy, and you find out this thing. Okay. So this is something we learned in our coordinate geometry course, and in this course we're going to do things in a little bit different fashion. We will look into the 3D world and define everything in terms of 3D. Okay. So let me delete this monkey head for now, and also get rid of the drawing as well. Alright, to keep things simple, I will go back to the grid view, and let's say we bring in a plane. The plane is too big, I guess. Well, not too big. That'll do. So over here, this plane is 2 units long on each side. It's actually a square. Alright. So what we're going to find out is how this thing moves when we translate, scale, or rotate this. Okay. To keep things simple, what I'll do is I'll actually delete all these things and deal with one part for now, and we'll change things as we go. Alright, so this is still a plane. We're still in 2D world, but let's see. I want to move to -1 and -half, I guess. Okay, so now it doesn't really look like a square anymore. I have changed the shape of it. Okay, and I did that on a purpose, and let me change this one as well, just so we can see the entire effect of scaling or translate or rotate. So, all right. So let's say we have this this particular plane, and we have this as Let's say this is 0.1, this is 0.2, 0.3, and 0.4. We can read up the coordinates for each of these points. It's very easy to do in Blender, right? You just click on this thing and it will say 1, 0.5, and 0. No big deal. Okay, so what I want to do is I want to make a copy of this so that I don't lose this. I duplicated that. And I want to scale it up to see what happens, all right? So S2. So what happened over here is that we have this original polygon, which is a quadrilateral, and we scaled it up. We made it twice as big. Okay? So we can see the original polygon right in the middle, and then we can see the new one over here. And you can sort of try to figure out what's happening. So let me write it down and let us validate whether the formulas that we found, they're actually working or not. So we'll start with the scaling one. That's what I did. This is -1, half, and 0, 4.1. And after the scaling, what we find is this is 2, actually -2, -1. This is actually -1, minus half, and 0. What we did over here is we used a scaling factor as Sx equal to 2 and Sy equal to 2. So scaling has a very simple effect. You take this factor, right? You take this factor and you multiply with the x component, and you take this and multiply with the y component. We're dealing with 2D right now, so that's why there is no effect on z. But what we would have in 3D world, if you can imagine, that we would have a sz component as well. So whatever the value it is, like in this case, if you're doing uniform scaling, that means that you're scaling on all the direction uniformly. You would simply multiply that. So we multiply -1 with 2, minus half with 2, and 0 with 2, and that's what we get. Is this thing clear? Okay. And the same thing goes for this point as well. This is 1, 0, 0, and now it becomes 2, 0, 0. This guy over here is 1.5 and 0, so it should be what? 2, 1, and 0. 2, 1, and 0. And it just works like that. So you simply multiply. Now, what if you have a varying scaling factor? So let me delete this one. All right. So we got this original polygon, and we will make another copy and scale it. But this time around, I want to use something different over here. I want to scale only on the x-axis, but not the y, not the z-axis. In Blender, it's really easy to do, so I duplicated, actually I moved it also. How do we do it in Blender? That I want to scale in the x-axis only, but not the y and z. S, x, and 2, right? So S, x, and 2, so that's what it is. But I forgot to duplicate this. Now you can see how this looks like, right? This is the original polygon, and here we have a scale version, but only the polygon is stretched on the x-axis, not the other axes. So this point over here, this -1, minus half, and 0 becomes -2, minus half. That doesn't change. So help me out. In terms of our math, what should be our Sy? And what should be our Sz? 0? 1. The scaling factor is if you don't want to scale on a particular axis, if you don't want to do that, then you put 1 in here. Because scaling is a multiplication. Okay. So if you want to make something bigger, you choose a scaling factor greater than 1. If you want to make something smaller, let me show you. Let us go back and undo this step if I can. I can't. So I'll just select all these things, Shift D, duplicate that again, and I will scale. This time I want to make it smaller, so I'll use a factor that is less than 1. So something like S.5 makes things smaller. This is half the size of the original polygon. Is this thing clear? Okay, so you can choose a factor which is less than 1 that makes things smaller. You can choose a factor greater than 1 that makes things bigger. And if you choose a factor that is equal to 1, what happens? It remains unchanged. Okay. So what if we go into the negative side? I want to delete these vertices. Let's say we got this original polygon, and I want to use a scaling factor, something like Sx equal to -1, and I will leave the other ones unchanged. What should happen then? I'm going to make a duplicate copy of this, and then we'll go from there. Yeah, it will be flipped horizontally. So Sx minus 1 gives you this view. And see if you can understand what happened right there. This entire picture, this entire polygon, whatever you have over here got flipped over in terms of the x-axis. Because what you're doing is you're multiplying the coordinates with -1. So whatever you had on this side, whatever value you had, like let's say this is +1, this would now become -1 because you're multiplying with -1. Why does this one doesn't change? Like this point right over here, the x value right there is 0. So whatever you multiply it with doesn't make any difference, just stays there. But for any other point, like if you had a point over here, on the negative side, it will come to the positive side just like that. Okay? So, let me delete this and let's try this one more time. I'm going to duplicate this, but this time around, I'm not going to pick any axis. I'll just say S minus 1. What happens now? This time it gets flipped on all the axes. It gets flipped on the x-axis and also on the y-axis. And obviously on the z-axis, but this picture is very much a 2D picture, that's why we don't see that. And it's not too difficult to understand that what happened over here. You see that the point on the top, it came right here at the bottom, because you multiply the y coordinate with -1, so it got flipped over. This point right here moved to that point over there, because this was negative x, negative y, and if you multiply that with the -1, both of them, they become positive and moves over there. So scaling, in essence, is really very easy to compute. You just multiply the components with the scaling factor. So let me write this down. We're going to revise these formulas, but you need to have a clear understanding, a visual cue of what's happening. So for scaling, if you are given a point with coordinates x, y, and z, after scaling, this thing becomes p prime, x prime, y prime, and z prime through a function a scaling factor, that is Sx, Sy, Sz. Okay. What we try to find out over here is how do we calculate x prime. We do that with x into Sx, y prime equal to y into Sy, and finally z prime equal to z into Sz. Is that clear? Okay. So one thing before I forget to do it, let me delete all these things. What would be the effect of using 0 as a scaling factor on any of these axes? Let's say I want to use 0 on the y-axis. So Sy0, it will get flattened out on the y-axis. Okay. And that's actually a very handy trick if you want to make something vertically aligned. Let's say these points, these 2 points are not vertically aligned, right? In Blender it's easy to make them vertically aligned if you just select them and hit Sy0, then they are aligned vertically. Okay. And for the same matter, like if you pick these 2 vertices and if you want to make them horizontally aligned on the x-axis, you'd say Sx and 0. See how that works. Or let's say I want to do it for all these 3 points, so Sx0, and now they're all horizontally aligned. So sometimes in modeling you're going to use these techniques, but they all belong to the scaling scenario. Okay. Now once we're done with scaling, let us look at the another easy one. Yeah, the translate. Okay. So for translate in Blender we have it with G, grab, right? So let us leave this original one in here and I'll just say GX1. So it moves along the x-axis by 1 units. Well, you can easily see this effect. At this point over here, move to this point only on the x-axis and not on the y-axis or the z-axis. Well, z is equal to 0, so it doesn't really matter at this point. Okay. Thanks. So we can move along the x-axis. We can also move along the y-axis if you want. So we just say GY, let's say 2, and it moves along the y-axis by 2 units. It moved away too far, but we can bring it down. We can go in the negative side as well. GX minus 0.5, yeah, moves like that. GY minus 0.2, well, GX minus 0.5, I forgot to hit enter, I guess. GY minus 0.2, works like that. So it's simply adding how much we're moving, right? Whether it's in the positive direction or the negative direction, if you just add the amount that you're moving, then we can find the actual coordinate for this thing. So let me actually copy this part. It's going to save me some time. It's hard to write with mouse like this. So what we're doing over here, we have the same sort of scenario that we have a point with coordinates x, y, and z, and we want to move to another point, P prime. But this time around, we're going to translate, and the translation amount is given as Tx, Ty, and obviously tz. Okay. So how do we find the formula for these things? That again is very easy. This is going to be x plus tx y plus ty, and finally z plus tz. Is this thing clear? Okay. Alright, so the final one, and I think it's better to do the construction over here, so I'll write it down. This is for rotation, and for rotation we have to pick a particular axis. Okay. Let's say we're talking about the z rotation only. It can be the x rotation, it can be the y rotation. It can also be rotation about any arbitrary axis, not just x, y, and z. It can be any axis that you define by yourself. So we'll start with the easiest one over here. Let's say we're given this polygon, and I'll just duplicate this. I want to rotate, and when I rotate this, we're looking at the xy plane. So whenever we are rotating, we're actually rotating about the z-axis. And if you look at a slanted view, and I think it becomes more clear, we'll say RZ, and then we'll rotate about the z-axis only. So the z value doesn't change. It's the x and y value that will only change. So let me make this thing really clear. When we move this thing about like this, the z value, whatever we have, will stay just like that. It's not going to be zero. It is what it is. It's not going to change. But the x and y values, they will change. We could also go for x rotation or the y rotation. Okay. So whatever axis we are rotating about, that coordinate will remain fixed, and we will imagine an axis that runs through that line, and it will move about that thing. So whether it's x, y, or z, it doesn't really matter. It can rotate like that. Or it doesn't have to be x, y, and z. It can be anything for that matter. So if I rotate like this, it's not actually about x, y, or z. It's about the axis that I am looking at right now, something like this. Okay. Now, when we talk about this rotation, if we want to find a formula for this, how do we go about it? All right. So let us just take this line over here and say that this point P, whatever point it is on this polygon, is some r units apart from the origin, and the origin is what we rotate about, right? So this is fixed. This is the origin O right here, and this is P. The distance OP is equal to the radius R. Okay. Now if I rotate this by some theta degree, right over here, that's theta. This point P prime over here would have the same distance from the origin. Can we agree on that? So OP is equal to OP prime, and they both can be represented with the radius, because when you rotate when you rotate a point around a particular origin, you can create a circle. So that's why we use R to say that this is the radius. Now, what we try to find out over here is, let's say, we're talking about the 2D part right now. We can move into the 3D world quite easily. Let's say the original point had coordinates x and y, and the new point will have points x prime and y prime. Okay. So what I want to find out over here is I want to have a function of x, y, and theta that would give me the values of x prime and y prime. Okay, I want to use these values. See, I don't want to pass the radius, because the way we are defining these points is through the Cartesian coordinates x and y. We're not defining it with r. So if you want to write a function that takes r as input, then that puts extra burden on the programmer or whoever is using this tool, because that doesn't really make much sense. R wasn't there to start with, right? We had x and y. Obviously, if you know x and y, you can find out what's the r. Okay. We will know theta for sure. That's why there is no problem including theta over here, because when you rotate something, you have to say how much you have rotated, like you have rotated by 10 degrees or 20 degrees, so that's also another input. So you give the origin, the location of the point, and you say how much you have rotated, and what we need to find out is what's the final destination. So in terms of x prime and y prime. Okay. Now this is better explained with r in there, and we'll see how we can remove this from the picture altogether. We don't want to keep r in there at all. So in order to do that, what we do is, let's say we have the x-axis running like this and the y-axis running like this. I know these are not straight lines, they're supposed to be straight lines, but forgive me for that. What we can say is that this point P originally is at some angle, say alpha or phi, whatever you want to use here. So let's say initially it was at an angle alpha already. It could be over here where alpha was 0, right? So no big deal, but right now we see that alpha is non-zero, for this point at least. And when it goes over here, what's the angle it creates? Alpha plus theta. All right? So that's what we have. Now if you understand this part, it's actually very easy to write this formula. See, for the original point, we can say x is equal to, no, r cos alpha rather. The angle over here is alpha, and x is the distance from here to there. So if you just use basic trigonometry, you can say x is equal to r cos alpha. We have actually done this quite a bit, right? So I think you should be able to recap that. And for y, we could write y is equal to r sine alpha. Okay? Now, if you look at the new point, which is P prime, what happens over there? X prime is equal to r cos alpha plus theta, because that's the angle, right? That's the total angle. And similarly, y prime is equal to r sine alpha plus theta, and that's that. Okay. Now what we're going to do is we're going to expand this because we don't want to deal with alpha, we don't want to deal with R. They were not there to start with. So we want to remove them from the picture. Okay? Do we know how to expand this thing? Cos A plus B. Help me out here. What's the formula for cos alpha plus theta? We're not sure? Well, at least, we need to memorize this part. See, we have that written over here. If you have cos A plus B, that's actually cos A cos B minus sin A sin B. For sin A plus B, that's cos A sin B plus sin A cos B. Okay, so for this one, this should be R cos alpha cos theta, and then minus R sin alpha sin theta. Okay. Remember, our target is to eliminate R and alpha from the picture altogether. We don't want them there. So given this expression right here, what can we do to remove R and alpha from the picture? We can use X and Y. Yes, we can do that. See, if you notice, X is equal to R cos alpha. Do we have that here? R cos alpha. Yes, we do. So we can write this as X cos theta minus, over here, do we have this part? Yes, Y sin theta, because here we got R sin alpha. So that's Y sin theta. Is that clear? So this is so much better now because now we only have X and Y and theta. And all these things are our input right here. So that's for X prime. Can we write another formula for Y prime? How do we go about it? We have to expand this, right? Sin A plus B is equal to sin A cos B and then plus cos A sin B. And now we are going to apply the same sort of technique we did before. R sin alpha, what's that? Y. Y cos theta. And over here we have R cos alpha, that's X. That's X sin theta. Is that clear? So let us just double check if we got them right. X cos theta minus Y sin theta. X cos theta minus 1 Y sin theta. That's the formula. And for Y prime, X sin theta plus Y cos theta. X sin theta plus Y cos theta. Is that clear? So we can write this down right over here. Let me copy this again. Actually, Over here we are applying the rotation so this is going to be a rotation about the z-axis by an angle of theta. So we write x prime equal to x cos theta rather. See, I forgot the formula already and I never have it memorized actually. And over here for y, this is x sine theta plus y cos theta. Okay. What happens to z? How do you write that? Z prime equal to what? Z. Because it doesn't change. So whatever the value was for z, you just type it in and that's what it is. So this is for rotation on the z-axis. Okay? When you rotate on the x-axis, things are going to be different. Alright, if you rotate around the x-axis, things are going to be different. See how we are rotating about the x-axis? To find out the formula for x rotation, what you have to do is you have to look at it from this side, where you have z coming out towards you, and here we have y, here we have z. Okay, so we have to redo the formula and then to come up with what happens when you rotate like that. If you want to do it for the y-axis, right, if you want to do it for the y-axis, this is how you place it. X over here and z up there, and you devise the formula again. Can we do it by yourself? Look at this picture. Well, actually, you have to look at it from this side. See, y rotation is a bit tricky because then x and z, x goes to the negative side. Z goes up there, but x is over here. If you look at the z rotation, both of them were on the positive side. Okay? If you look at the x rotation, both of them are on the positive. If you look at the y rotation, x is on the negative side and z is on the positive side. Okay. That will affect a few things. So this is for z rotation. Let's see if I can find the formula over here. 3D rotation formula. Yeah. See, for the x rotation, this is the formula. I mean, it's written in terms of q, not theta. But it's the same thing, doesn't really make any difference. This is y cos q minus z sin q, y sin q plus z cos q. For the y rotation, this is what we have, sine and cos. And for the, where was the z? Z was up here. Cos minus sine, sine plus cos. Cos minus sine, sine plus cos. Cos minus sine, sine plus cos. something is not right. Just a bit. And that page that I looked at is definitely not right. It's written in a slightly different notation. I will talk about the matrix representation, but at least what you see over here, this is for x, this is for y, and this is for z. We are rotating by theta degree. It's written in matrix form, but you see this is cos minus sine, sine and cos. For y, this one changes. This is cos, not minus sine. This is actually sine. And this becomes minus sine and cos. For the z, it's the same thing, cos minus sine, sine and cos. So the one in the middle, you'd have a different formula for that, because it has x going on the negative side. So try to find out these formulas for yourself at home. I only did the z rotation, but if you understood the construction of the entire thing with alpha and theta, you should be able to do that on your own. Is that clear? Okay. So let us try that, and we'll see how we can go from there. Alright, so if we understood that bit, let us go into something a bit more fun. Okay? We'll try to do a bit of animation over here. We know about the solar system, right? In our solar system, we got a sun right in the middle, and then we have the planets orbiting around the sun. Okay? How many planets we got? And let me count over here. 1, 2, 3, 4, 5, 6, 7, and 8. See, when I was a student in primary school, we learned that there were 9 of them. I mean, there was Pluto there, but then they kicked it out. It's no longer a planet. Okay, so things change over time. And also, my knowledge of the solar system has also changed over the time. See, let me draw a very crude figure over here. What we know about the solar system is like we have a sun right in the middle, right? And then we have the planets orbiting around it in some elliptical path, right? It's not entirely circular. So something like this. So let's say we got a planet over here that orbits like this. There will be another planet that orbits like this. They may have different sizes, these planets. They may have a different orbit path, but this is how it goes, right? And what we imagine is that the sun is right there, it's stationary, it's not moving. It's the planets that are actually orbiting around the sun. Okay. What we do know is, like, let's imagine that this guy over here is our Earth, and we have a moon that actually orbits around the Earth. And there are other planets that have one moon or multiple moons. Jupiter, for example, I think has 2 moons. I'll have to check that though. So, depending on the planet, you may have 0 or n number of moons that are orbiting the planet itself, and the planets are orbiting around the sun. All right. What happens about the sun itself? So let me see if I can look at this video. Right, yeah, I'll be playing this one. Let's see if I got sound up. I think that serves the purpose to say that, well, this is not just stationary. The sun is not stationary, it's moving, and all these planets are actually orbiting around it, and it's also moving at the same time. This is a quite interesting video because it talks about the vortex and how the nature is also inspired by it. Let me go forward over here. So we see vortex all around us in many different forms. These are all vortexes. They come in spiral forms in our nature. Okay, so this video tries to relate the concept of the helical system into this. But that's not really my point. What I'd like to do over here is we'll have a very simple animation of maybe a stationary sun, and we'll have the other planets, the 8 planets orbiting around it in, let's say, circular fashion. We can certainly make it elliptical, and then we can also throw in some moons around that so that they move around that object. Okay. We can do this animation in Blender, of course, and we can also do this animation in the OpenGL program. We'll learn how to do that, but later on. So what I want you to understand, even without doing this animation, I'll see if I can do this animation right now. Well, not right now, I mean maybe in the next bit of our class, like our first class is going to end in a bit. Let's say we have a sun right here. So we will, we can bring in a UV sphere like this. That's going to be the sun, right? The planets are much smaller than the sun. Right? Okay. So if I keep this as the sun right at the origin, let's say this is stationary, it's not moving. When I bring in, let's say, our planet Earth, that's going to be another UV sphere, but it has to be much smaller in size. Okay, even smaller than that, but I'm not going to make it even smaller. Okay. So what sort of transformation did I just apply? By the way, I forgot to mention the most important thing about today's talk is we're talking about scaling, we're talking about translate, we're talking about the rotation. All these things, they are called transformations. These 3 things, they're called transformations. And to be specific, they're called affine transformation because they maintain the affinity. Affinity, it means togetherness or being close to one another. So when you look at these affine transformations, did I already lose my Blender file? Yeah. Okay, all right. Let me leave this here. So let us take this plane over here, and if I scale this, let's say this is vertex A and this is vertex B. If I scale them, even after scaling, vertex A prime and vertex B prime, they will still be attached to each other. So they will maintain the affinity between them. So scaling doesn't destroy the affinity, neither does rotation, neither does translation. So all these three transformations, they maintain the affinity. That's why they're called affine transformation. Okay. There's another important affine transformation that I never cover. Let me just mention the name. It's an important one. It's just that it's not as important over here in terms of 3D animation. This is called shear. So let me just draw a figure to show you what shear is. Let's say we got a rectangle like this. In many desktop editing tool, you will find the shear tool with which you can move two vertices in one direction like this. Okay, it's not actually rotating the whole thing, it's moving a part of it towards one side or this side. So that's actually the shearing. It comes in handy, like let's say we have the letter A and I want to have a italic version of it, which looks like this. So that's where shear may have application. Well, it does have application. Okay, but I'm not going to go through the formula for shear. If you're interested, look up any textbook on computer graphics or the math books that I refer. You can find the formulas there. But that's also another affine transformation. Why I don't cover it over here is because it's not going to help me with the 3D modeling in most cases, and also the 3D animation. It doesn't have much application for that. Although obviously you can invent a few. Okay, so as you can see right here, since this is C3 view, the wireframe view, that we have a scaled version of the sun. So if the sun has radius 1 unit, this has much lesser radius, let's say 0.2 units. Okay. So that's a scaling effect. This Earth right there is going to move around the sun, right? But another thing, Earth actually moves around itself. There is a axis set for the sun, set for the Earth, and it's going to rotate on its own axis. It's not the z-axis. It's actually tilted by how much? It's too bad we don't have any course on geography in computer science. 23.5 degrees. I mean, that's why we have the difference in days and nights. The length varies as we orbit around the sun. Okay. So what I mean by that is it's actually tilted like this, and then it rotates about that tilted axis. It rotates like that. You must have studied that in primary school maybe. Okay. All right. So that's one thing, right? So the Earth orbits around rotates around itself, and what it does next is it orbits around the sun like this. So as it's going around the sun, it's also rotating around itself. Okay. And this is where you need to understand that in order for this to happen, it needs to get translated first and then rotated. If you rotate something first and then translate, it's a different effect. See, if I rotate this first and then if I translate this, it just moves like that. I will have the rotation effect, and it will stay right there. But if I move it away and then start rotating, I will have something like this. So imagine that you have a heavy object, you tie it with a rope and take it in your hand and start rotating like that. So it's going to orbit around your finger or your hand if you're holding that. But if you just keep it on your hand, if you rotate it and take it to some other place, it's not going to change anything, right? You have the initial rotation and you take it over there. Or you may have it spinning and then you just move it away. It will stay right there and keep on spinning. It's not going to move around you. So there are two totally different things. If you rotate first and then translate, versus if you translate first and then rotate, they're not the same. Okay, so you need to understand the difference. So when we come back after, let's say after 15 minutes, I'm letting you go a little bit early, that's why 15 minutes. So let's take a break. We'll come back after 15 minutes. We'll try to see this in animation, and we'll try to see what happens over here in terms of math. Okay? How we can write these things and how we do these things efficiently in Blender or any other 3D modeling tool. Okay. So I'll just finish recording this part and then we'll add on to this.